Our next optimization problem, there's a real estate company that owns 100 apartments. They can rent them for $1,000 a month. However, for every $50 increase, there will be 2 additional vacancies. How much should they charge to maximize revenue? One of the hardest things is coming up with the function for revenue sometimes, but notice that if they charge $1,000 per month, then their total revenue will be the 1,000 will be multiplied by 100 to get the total revenue. And if they increase the rent by $50, then they're also going to lose 2 customers. So that's what the revenue will be. And if they increase the rent a second $50, then they will also lose another 2 people. And if they increase it a third $50, then they will lose another 2 people. So every time they increase the rent $50, they lose 2 people. So a model for the revenue then is 1,000 plus 50x, where x is the number of revenue increases, and times 100 minus 2x, because they always lose twice the number of people. I'm going to use the product rule to take the derivative of this since I want to find the maximum. I could multiply this out, but I'll just use the product rule. In this case, the derivative of the first is 50, and that'll be times 100 minus 2x, plus the first function, 1,000 plus 50x, times negative 2. Now cleaning this up a bit, the derivative must equal 5,000 minus 100x plus negative 2,000 minus 100x, and so the derivative is equal to 3,000 minus 200x. I'd like to know when this equals 0, and solving for x, we'll find that this will equal 0 when x is 15, which means we'll be making 15 $50 increases. And just to verify, if we do some sign analysis, if we use the number like 10, we get a negative number. No, when we use 10, we get a positive number, and when we use 20, we get a negative number, so it is a maximum. That's how many $50 increases there will be, which means that the rent will, to maximize revenue, will be $1,750. Let's look at a second problem. There is a box whose volume is 1,800 cubic inches. So this box has a square base. So its base is x squared, its height is y, and its volume is 1,800. And notice that this means that y must equal 1,800 over x squared. Now there's something about this box to make it. The top and bottom, whose areas are x squared, cost $3 per square inch. So the cost of this thing for top and bottom will be $3 times the top and bottom's area. There's 2 of them, that's why it's 2x squared in this case, plus the cost of building the sides. There's 4 sides. The cost will be $1 per square inch, and the 4 sides have an area of x times y, so 4xy. Cleaning this cost function up and putting it in terms of x, our function is 6x squared plus 7,200 over x. Since we would like to find the minimum cost, we need to find the derivative of this function, and that will be 12x minus 7200 over x squared. The derivative equals 0 when 12x equals 7200 over x squared, or when x cubed equals 600, or one side length of this cube will be the cube root of 600, and that's about 8.434 inches in this case. The other side length is that number. How many times does that number go into 1800 when I square it? So what is the cube root of 600 squared? And then divide by, if I put that number into 1800, and you get about 25.303 inches. So that tells us about the box. It'll be 8.434 by 8.434 by 25.303, and the minimum cost then will be what I get when I substitute that back into the equation, and it is about $1,280.48. So we've got a minimum cost and the dimensions of our box.